questions from yesterday's lecture. I always bring a question or two of my own. Of course, the question in my mind is, which slide exactly did we end at? Let's think about isobutane. If we had a N.M.R spectrum of it, how many signals, peaks, would you see? What do you think the first thing you need to do to solve a question like this? Draw the structure, absolutely. Well, that looks about right. So how many different types of hydrogens are there? Absolutely. There's two types. Let me label these A, and this one I would label B. Draw the spectrum showing the intensity and shift with no peak splitting. We haven't talked about peak splitting yet. We're going to talk about it now. Not exactly now, in a few minutes when we get to the slides. So yesterday we looked at a methylene hydrogen, a methine hydrogen. Is there a methylene hydrogen in this compound? No. Is there a methylene hydrogen in this compound? Yeah, there it is. Is the methylene hydrogen downfilled or upfilled of the other hydrogen? Very good. It is downfilled. So there's my little TMS. What's that stand for? Trimethylsilene. One of my favorite quiz questions is draw the Lewis structure of TMS. All right, so that's the furthest upfilled. All right, so there's going to be two peaks, and you've told me the B peak is going to be about there. That means the A peak has to be about there. So that's the shift portion. Draw the intensity. What's that mean? How many hydrogens are represented here? 9-to-1. This will be very scientific. There's the expected N.M.R spectrum with no peak splitting from maybe what we learned the other day. We left off looking at the table of chemical shifts, and it said where these things absorb was somewhat variable, and that's due to this thing here. The chemical shift of the acidic protons depends on the concentration. Hydrogen bonding in concentrated solutions de-shields the protons. And so here are the chemical shifts for hydrogens on a nitrogen and hydrogens on an oxygen. Proton exchanges between the molecules, broadening the peak. So one way to check if you see a peak and you think, oh, that's an alcohol peak, if you can pull the N.M.R tube out and dilute it and see that peak move, that confirms that hypothesis. So good old acetic acid, how many signals do you think we'll see? Well, how many different types of protons are there? There's a group, they're all chemically equivalent. There's another group, and this thing I think is drawn off the plot. That's why it says it's almost down here at 12. And we might see a 3-to-1 ratio. Because of the high polarity of the carboxylic group, the OH bond, the signal for the acidic proton will shift and is greater than a delta value of 10. Methyl tetrabutyl ether. How many types of protons? We just see two types of protons, so we see two signals. Chemically equivalent hydrogens have the same chemical shift. These are all chemically equivalent, because if I made the model, I'd rotate that bond and you'd see these precess around, and you can't differentiate that one from that one or that one. That's what it means to be chemically equivalent. All right, slide. So these little traces is when the machine integrates, finds like the area under the curve. We can call that intensity, how big a peak. So we call that integration. Integration will have a trace for the tetrabutyl hydrogens that is 3 times this one. So the machine doesn't say 3 to 9, it'll just give us this 1 to 3 ratio. And it's up to us to figure out, well, if this is a methyl group and I got 3 protons there, I probably got 9 over there. So here's the fun part of today's lecture. It's this thing called spin-spin splitting. So let's just see if I can go back quickly. Oh, with the N.M.R chapter, I can review this slide at the beginning of each lecture. This is what I first asked you. The number of signals shows how many different kinds of protons are present. The location shows how shielded or de-shielded is the proton, gives us the chemical environment, tells us an awful lot about the structure. The intensity of the signal shows the number of protons of that type. So now we're going to get into this fourth topic here. Signal splitting shows the number of protons on adjacent atoms. What is spin splitting? Well, we already decided that a proton, since it has charge and since it has spin, it's a tiny magnet. So these tiny magnets can affect the other tiny magnets. Non-equivalent protons on adjacent carbons have magnetic fields that may align with or opposed to the external field. This is called magnetic coupling. It's going to cause the proton to absorb slightly downfield when the external field is reinforced and slightly upfield when the external field is opposed. All possibilities exist, so the signal is split. This splitting of signals into multiplets is called spin-spin splitting. So 1,1,2-tribromoethane. There it is. I see two types of hydrogens. There's the hydrogen on this carbon, and I see the hydrogen over here. I'm going to see two signals. Here they are, but these signals get split a little bit. This thing we call a triplet, and this thing here we call a doublet. I apologize for the poor graphic. I fixed up a couple later on. Spin-spin splitting is a reciprocal property. If one proton splits another, the second proton must split the first. What that means is this proton is splitting these protons is splitting that one. This thing acts like a magnet. It can reinforce or oppose the magnetic field that these two feel. The magnetic field that these two protons feel can be reinforced or opposed by this thing acting like a little magnet. So when we see a doublet, a peak that's split into two, that tells us that there's one proton on an adjacent carbon. That's what it tells us. And so here we draw, here's the magnetic field. Here's this thing drawn as a vector, its own little magnetic field, and it reinforces the field that these see and it absorbs there. Now it's pointed down, it opposes the field, and we don't really need to concern ourselves whether we can differentiate which is which so much for this concept. The main thing is when we see a doublet, we know it's being split by one proton. Now we see a triplet. So here, if both these protons are pointing this direction, it's reinforcing the field. If both these are pointing down, it opposes the field. Here, one's up and one's down. How many of you like binary numbers are figuring out all the options? That's kind of how I think about this. But notice here's two probabilities. Here's just 1 and 1. All right, so notice this is taller. That's this point here, number 3. It is more likely that one of these will be aligned to with and the other against. And so that's why this thing is a bit higher and we get this thing called a triplet. So now we get to this thing called the N+1 rule, which might say if a signal is split by n number of equivalent protons, then we're going to split the signal into N+1 peaks. So take that back to the doublet we just saw. We had one equivalent proton. 1 + 1 is 2. So here's a singlet, a doublet. So this is n. 0 + 1 is 1. We see a 1 + 1 is 2, and we see a doublet. Well, I'm out of time, so I'll let you go.